Well, today, boys and girls, we're going to be boys, I guess, right? We're just going to be talking more about systems, some more of the basic generalities of how these things work, and how our solutions will be working. We mostly we're going to be in Chapter 3, actually, I've decided. Some of this Chapter 2 stuff is more of a broad overview upon looking at it further. And then there's a couple, toward the end, there's an epidemic one I think is kind of cool. We'll come back and look at that, and Lorentz functions. We'll come back and look at those are some specific types of systems. I think we'll look at those later. After looking at this weekend, I don't really care how this book's laid out at all. So I think we're just going to go into Chapter 3 and get going a little bit on it. So the game is this. As we mentioned the other day, you're going to have dx dt is equal to 2x plus 3y. And dy dt is equal to, or whatever. Okay. Now again, a lot of books will do it as dx1 dxt is 1 plus 3x2 dx2 dx dt rather is equal to 2 or negative 3x1 minus 4x2. Your book, for whatever reason, decided to use y instead. I don't really care, but the basic gist of it is this. They take this guy here and they turn it into this. Big dx dt is equal to some a times some y. Now what is this? Well, this is on a matrix of coefficients. And so 2, 3, negative 3, negative 4. No, negative 3, stupid. Times the matrix, times the vector, we'd actually say y, because the vector is a 2 by 1 vector, which I guess if you want to write this way, would be y1, y2. You could think of it as being, well, the way I have it written right now, it should be x1 and x2. Your book, as I say, uses y's instead. But that's all they mean when they write it like this, is they've turned it into a matrix times a vector. Okay? Which, of course, when you distribute it out, gives you back to this business right here. Now, as we mentioned last time, and we kind of jumped right to the final solution, and that's this. X of t is equal to something times a constant times my first function. So it's going to be some e to the, I don't know, kt or something. And y of t will be of the function something along these lines as well. But the question is, why is it that way? Well, here's the game. Okay, each one of these pieces, e to the kt and e to the pt, are both solutions. Okay, so what we end up having is that this function by itself, this piece right here, actually does solve both equations by itself, obviously with some sort of a constant in front of it. So does this piece here. Okay, but when we add them together, we call that a linear combination. And they form what's called the principle of superposition. It's very similar to back when you talked about this in physics, because all of you remember taking that. We had a function that was doing this, and we added another sound function that was doing this. And what did it do? Well, it just made this kind of do this thing here. It didn't really do much to it in this case, but it kind of made it squiggly. In other words, you added them to them. Now, obviously, if you added this guy to it, you'd get a big fat 0 because they'd cancel each other out. Okay, that's dumb and lame. We won't be doing that. But if you added this guy to it, well, this plus this here wouldn't change, obviously. This plus this would be negative, so it'd be up to here-ish if you're adding them. This plus this gets a little bigger. This plus a negative looks like it gets a little more negative, actually, maybe like that. I don't know. I just work here. This plus this, that's huge. You with me on this? And then this and this pretty much cancel out. I'm just eyeballing it here. That's all I'm doing. Yeah, so in here somewhere they're equal to 0, which is where I've crossed it at, of course. And then here, this plus this, well, it's positive again, so we're back up to here somewhere, and so on. And the idea is you just add these two functions together. That's called the principle of superposition, and the fancy way of saying it is they are a linear combination. Okay? Now, what does that mean? Well, it's important that those two functions, e to the kt and e to the pt, are what we call linearly independent. Now, there's a possibility that maybe you have something in front of this e to the pt. I mean, it could even be another function here like t. Ooh, cool. We'll get to that one later on. The idea is these are not the same functions. With the t in front of it, these are no longer the same functions either. What you can't have is they can't be the same function, and it's a principle that we have to adhere to of linear independence. Now, we'll actually look at that a little more in depth later on. Suffice it to say, the first few that we do will already be set up that way, so I'm not going to worry about it too much right now. We will come back and spend some time on that, because without independence, we are hoped. And I just checked. I wanted to make sure this guy had nice eigenvalues, and it does. So once we have this situation, we talked about it, we can rewrite this as big dx dt is equal to 3, 6, 1, 4 times big X, right? That is a vector of X. And the idea is we need to find the eigenvalues. Now, I'm going to ask that you do these by hand, of course. But did you show this on the calculator? Well, no, I did. You're not wrong. But I want you to get in the habit of doing them this way for a while, and we'll let you use them later as well. Especially when they get gross later on. We're going to go ahead and do that. Now this is lambda squared minus 7 lambda plus 12 minus 6. So this guy right here is the characteristic polynomial. And it has zeros, of course. That's the whole point, at 6 and at 1. So these are my eigenvalues. So we know that the solution will look like this. X of t and y of t will look like c1 with something in front of it, e to the 6t, plus something, c2, e to the t. And remember, this thing here is an eigenvector, and this thing right here is an eigenvector. This one is associated with 6. This one is associated with the 1. Okay? Now, again, how do we find them? Well, we come back up here to this fella, so it's 3 minus lambda. And, 6, 1, 4 minus lambda. And one at a time, we stick in our eigenvalues. So let's put in lambda equals 1, for instance. All right, whatever. So that's going to be 2, 6, 1, 3 times some a and b. And the trick is it has to equal 0, 0. So that's 2a plus 6b equals 0. And obviously a plus 3b equals 0 is the exact same function. So any value that makes this top one work makes the bottom one work as well. So I'm saying 3, negative 1. Are you with me on this? So that's going to be 3, negative 1. Now let's try it with 6 just for fun. Well, because we have to. And so that's going to be negative 3 and negative 2. So negative 3a plus 6b equals 0. Of course, the bottom one's the exact same function. So if I do 2, 1, that ought to work. And we're home free. This, by the way, is the generic solution to that equation. That is the generic solution. It is the general solution. If that's all we were told, that's all we can do. However, I'm going to make up some values here. So if that were true, then if x naught was what did I say, 7, and y naught was 12, then 2c1 plus 3c2 is equal to 7, and c1 minus c2 is equal to 12. That's what we said, right? Nice. So do some math here. Times the bottom one by 2. for instance, you get 24. Subtract, you get 5. C2 equals negative 17. C2 is negative 17 fifths. Yeah. And, you know, there's several ways to go. You can put it back into the original function. Right? Well, that's 60 fifths minus 17 fifths. 43 fifths. So my final answer would be 2 times 3 is 43 is 86 fifths. E to the 6t plus, oh, it's actually going to be minus 51 fifths. E to the t, it's x. And y would be 43 fifths. Notice again it's half of the top one. And then minus a minus, a plus 17 fifths. E to the t. And that is a 3-to-1 relationship. So, yeah, buddy. And we're home free. Now, as I mentioned last week, we're going to look at phase plane plots again, or phase plane portraits, as they are often referred to. Phase plane portrait grapher online. Now, I know we saw this one last week, this one I'm going to show you, but I figured out kind of what it was. It was stupid because last week I'm sitting there going, why is this doing what it's doing? But then I realized what it was doing, and I got really excited about it. Because check it out, dude. Oops, stop it. Don't do that. Stop it, stop it, stop it. This is your matrix right here, A, yo. And so our A matrix had, what do we have? So notice what I'm changing down here. I'm changing this far one right here, this bottom guy. And so what I'm looking for is I'm looking to match up this A matrix here, this companion matrix they call it. Okay. Now, so what I'm doing here when I'm moving this guy is I'm changing what my determinant is, of course. I'm trying to get my eigenvalues to match up. Do you see that? There they go. Now, my eigenvalues were both positive. Now, I don't think I can get out to where mine were, but it was something like, what were my eigenvalues? Something like, 1 and 6, correct? So what we're going to see is we're going to have what's called a nodal source, okay? And so I wish I could move that out a little further, but I can't really. So we're going to spend some time this week discussing, well, what happens when you have eigenvalues. Eigenvalue 1 is less than eigenvalue 2, and they're both greater than 0, let's say. So they're both positive, but they're unequal. And we're going to talk about what that is, and it's going to be a nodal source. It's always going to have this same general shape like this. Everything's going to emanate from that location, and it's going to have some general shape looking thing to it like so. In other words, if you started right here, that's where we go pew, 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 pew. And what you're doing is actually basically graphing a solution. You see x right here, x versus y. Okay. Now, you can do this several different ways down here. This down here changes the A, B, and the C's of your matrix, yes? And then now that I see what I'm doing, I know what I'm doing even better now. I didn't realize that could be changed. So, my equation was, my matrix was, let's go back up one. It was 3, 6, 1, 4. Now, I don't think this goes out far enough, but 3, right there. 6 doesn't go over far enough. Darn it. 1, 4. Okay, so ours looks basically like that. And again, you can see there's your eigenvalues. They look similar, except notice that this is a saddle point. And the reason for that is because I can't go over far enough on this one to get over to 6, okay? So I back this one off a skosh. Oops. This one maybe. And we'll see that nodal source look. The problem again is I can't change this to exactly what I want it to be in this guy. I wish I could. But it's kind of neat how you can move these guys around. This is your A, that's the top one, that's this guy right here. B is this one right here. And then C and so on and whatnot. Okay, so there's that. So you can move these guys around and see what's up. Get them kind of where you want them. No, I lied to you. Oh. Well, this, you can change your C and D down here, I guess. That's what that is. It does change C and D. Well, why aren't these changing? Well, interesting. Well, anyway, so but stick with me. You'll see what I'm talking about here in a minute. Now, what happens if both of your eigenvalues are both negative? Well, it would stand to reason that they would be similar situation, except that, you know, obviously it's nodal, but this is going to be the case where they're both like this. Well, everything's going to be collapsing, yes? So it's going to have the exact same idea, except it's going to be a sink. And you can see that from this picture over here. We can make it so that both of them are negative, and you can just screw around with this until they both end up that way. Oops, move these guys around a little bit. Oops, not that one. Move this one back over here. Oops, come back over. Come back this way. No. For crying out. Oh, no, there we go. Right there. Yeah, baby. So here they're both negatives. That's what I wanted. Yes. And again, I have this idea that it's a nodal sink. Everybody is collapsing to this value. If I start here, boom, into there she comes. Notice how we're all coming in parallel. All of these trajectories, we say, are coming in parallel to one another, yes? Pew! Parallel into that collapsed point. By the way, where is that collapsed point, that equilibrium, if you will? Well, come back here, yo. What are the values of x and y that make this happen? 0, 0. And that is why everything on this picture is headed towards 0, 0. Boom. Okay? Well, now you're thinking, well, wait a minute. What if I have one's positive and one's negative? I don't know. Let's find out. And so if you do that over here, it's pretty clear as soon as you move them around until you get that. No. Come back. Come back. Oh. One's positive, one's negative. Check it out, dog. It's a saddle point. Now, what does that mean? Well, it means this. Means that as one's getting larger, one's getting smaller at the same time. So, for instance, if you had e to the 6t and e to the negative t, well, near zero, this one is bigger than this one. Near zero. Okay? But as soon as you get away from zero, this one takes over and does all the driving. That is, it comes down almost to a minimum and then back up again. And you can show yourself that, of course, by going to Desmos.com. Come on, give it to me. Give it to me, you hippie. Come on. Oh, I don't know. Negative x plus 3e to the, oh, I don't know, 2x or some such. Look what's happening, friends. It's like it's coming down. It's like it's headed down. Whoop, and then see ya, we're out of here again. And that's what's going on with this saddle point. That is, you're coming down, you're approaching some value, and then you shoot off again. And again, what's our value here? Well, again, our value is at 0, 0. Okay? So that's the game with that guy. Now, you say to yourself, well, wait a minute. Both negative, both positive. What if they're the same, Mr. Grimm? What if they're equal to one another? Oh, I don't know. That's a good question. Could we pull that off? I don't know. Probably. Give it to me, you freaking hippie. Now, we'll see if we can make it happen on this deal. If we can't, we may have to wait. I can tell you. Oh. Ah, fart. Come on, give it to me. Stop it. Now, it's a defective nodal sink. Defective, Mr. Grimm. Why defective? It's a good question. Well, we're going to study this one actually in quite a bit of detail when it comes to an application situation. What ends up happening is this. If you had this scenario, in this case they're both less than 0, by the way. Okay. In this case, so it's a sink, of course. But what's going on here? So the idea is this. Well, if they're the same, you'd end up with this, like, I don't know, something like 5e to the negative t plus 6e to the negative t. Wait a minute. These suckers are not linearly independent because, that is the same as this. Ooh, that's weird. And so a rule that we're going to learn in the next few days is this. When you have repeated roots like this, one of your solutions will be of the form, C1 e to the lambda 1t or whatever, because they're the same, plus C2 t e to the lambda t. Okay? And because they're the same, I don't really need to label them. Okay? Or some books write it this way. This is actually a very important concept. Okay? And when it comes to dampening things, this is a very important concept. We'll talk about him a lot. But again, notice what's happening. If it's less than 0, this sucker is going down to 0 quickly, yes? It's petering away. So this one is a sink. Of course, if it was the other way around, of course, it would be a source, but same basic premise. Now, of course, that's that. Of course, then they're just quadratics. So, I mean, the only thing you could be is it could be greater than 0, less than 0, one of each, equal to each other, or my personal favorite. Well, oh, look at that, dog. They are both what? Imaginary. Shut up. They're both imaginary. So notice my real part is negative 1.27. And then it's this 0.194 business. What that's going to do for us, as we mentioned previously, if you have a plus or minus bi, and a is less than 0, what we're going to have is we're going to have this spiral sink. Everything is collapsing to this sink, to this point down here at 0 in this case. Okay? Because it's going to be an e to the negative at or something like this, cosine bt plus, and then, well, okay, so it's just me, basically plus a sine of bt. In a minute, we're going to, and not today, in a few days, we're going to talk about, well, what do we do to combine this, because it's an I sign. You're not wrong, but we're going to look at that a little bit more in depth later on. What if it's a plus or minus bi, and a is greater than 0? Well, then it's going to be doing the same thing, except it's going to be exploding out from here. So we're going to call this a spiral source. Okay? And then, of course, what if it's just plus or minus bi? Why, then it's just going to be this, what we call a stable center. And this picture actually shows it over here when we do them. So you can actually make that happen if you're good. That's pretty cool. Oh, that's still a source, but you can see if this was 0. Oops, stop it. One could see if that was 0. Stop it, you pig. Well, you could see it happen there for a second, right? I think you could. I got this baby right at 0. Yeah, there it is. It's a stable center. And that is plus or minus 1.35 I, or 1.58 I. Okay, it's perfect. And then, of course, you could go, drag it around to where you have, over here, we have a spiral source because our A piece is positive, and then we got some cosines and sines going on. Okay, now we are going to do a couple more easy ones tonight to practice doing these, defining these solutions. So here's another one. I think I'm going to pause you so I make sure I get it to work out correctly before we begin, because I would really hate for this to work out gross. Then you get all mad at me and Jacob starts crying. Or Levi would have a fit. I'm not sure which one it would be. Anyway, so I have a situation here like so. Again, remember this can be rewritten as basically dx dt. And I'm going to use x's and y's because I really do. I get confused easily when I use x1 and x2. You drop one of them, then you're not really sure where you are, and it's just a mess, okay? So this is a times x right here. Okay. So that's 2 minus lambda 8, 1, 0 minus lambda, which of course, if you do your characteristic polynomial, gives you this minus 8. That's lambda squared minus 2 lambda minus 8 equals 0. That's lambda minus 4. That's lambda plus 2. 2. That's negative 2 and positive 4. This means we're going to have a saddle point here. because as 1 gets bigger, 1's getting larger. So we know that we're of the format e to the 4t with the c1 in front of it, and then plus a c2 with something in front of that, and then e to the negative 2t. Again, this could also be rewritten as just x equals c1 times our vector e to the 4t plus c2 times our vector e to the negative 2t. Same difference. Now, let's move on from this business here. Now, let's come back up to this guy. So 2 minus lambda, 8, 1, negative lambda. And let's slap in our eigenvalues one at a time. So our eigenvalues are 4 and negative 2. So let's do 4 first. So 4 would be negative 2, 8. That's going to be 1, negative 4. Clearly the same this time, 100% the same. Nothing to worry about here at all. So I think 4, 1 would get the job done. Okay. If you put a 1 in there, you're going to get 1, 8, 1, negative 1, which is creepy. Something screwy there, pal. Oh, because it's negative 2, you jerk face. What an idiot, yo. Yeah. Alright, because remember, that has to work, dude. It has to work. So if it's not going to work, like 1 and 8, 1 and 1 ain't going to happen, try the actual value, stupid. So like 4, 8, and then like 1, 2, like, okay, you know. And alright, here we go. Whatever. So 4a, so 2 negative 1 gets the job done, yes? There we go. And so then the question is, what was our initial values? Oh, geez, I didn't write them down. So x of 0 is 1 and y of 0. 0, let's say. I don't know. 1, 0. Sure. 1, 0. Well, that means that 4c1 plus c2. Oops, wait, no. Plus 2c2 equals 1. And c1 minus c2 is equal to 0. Nice. Okay. My leg went to sleep. That's no fun. Let's times the bottom by 2, I guess. And then just go ahead and add, I guess. I get 6c1 is equal to 1. Stupid. So c1 is 1/6. And ouch. That kind of means that this was c1 minus c2 a minute ago, right? Had to equal 0, so that means they have to be the same. So they're both 1/6. So this is a fine way to write the solution. Or if you prefer, that's 2/3 e to the 4t plus 1/3 e to the negative 2t is equal to x. And then 1/6 e to the 4t minus 1/6 e to the t negative 2t, stupid. Judas Priest is equal to y. And away you go. Okay? Sure. Let's do one more. I think. And so, Ooh, fake you out. No big deal, yo. Well, I'm tired of 6y. I think, let me pause because I want this to work out nicely and cleanly, so just pause. Alright, tweak to the skosh. Oh, let's go back to the other one just for a minute. Notice that we had here, we had this 2810 business. Oh, I can't graph that on the other one. Well, we'll graph this next one because I think it works, maybe. Oh, I put a darn 7 in there. Just a moment. Alright, so this one should work actually. So let's go look at it. Okay, and again, so I'm not sure what's going on with that guy. Well, we'll see in a second what kind of solutions we get, and then we'll come back to that, I guess. So 3, 4. This is 3 minus lambda, of course, and then of course we're going to get 3 and -1 minus lambda. So if we do our characteristic polynomial, lambda squared minus 3 plus 1 is -2 lambda, and then you're going to get a minus 3 minus 12, so you get lambda squared minus 2 lambda minus 15 equals 0. It's lambda minus 5, that's lambda plus 3. So -3 and 5 are my lambdas. So again, we got a saddle point action going on. Darn, my eye hurts. Okay, so I know that my form is of, I'm just going to write this way this time, big X is equal to C1 e to the 5t plus C2 e to the -3t. So let's see if we can do it straight from here. If we put a 5 in there, we're going to get -2 and 4. And you're going to get 3 and -6. So that's a 2-to-1 relationship, yes? A, B, 0, 0. So -2a plus 4b equals 0. So I want this one times 2 and that one times 1. So if you put in a -3, you're going to get 6, 4, 3, 2, which gives the same relationship. Alright, so then you're going to have, well, the easiest way to do this, of course, is just to go, well, 6a plus 4b equals 0. And then realize that you could times this one by 3 and this one by -2, or vice versa, and they would work. So I'm going to use -2, 3 this time. Could have easily just used 4, -6 would have worked. Any of those would have worked just fine. Okay? So no initial condition here yet. So again, if there wasn't an initial condition, you could stop right there. If there is, like this one, we're going to keep going. Let's see, what's up, homie? Oh, let's don't do negative. That's gross. 10. Go away. No one asked for your opinion. So remember, that's 2c1 plus, or minus rather, 2c2 has to equal 7, correct? Because that's the top line. Right? That's one equation. And then there's also the, the bottom line, which is here times here times here times here times here, right? That's the second equation. So that would be C1 plus 3 C2s is equal to 10. Again, your favorite way of solving these makes me no difference at all. So perhaps you want to times the bottom one by 2 and then subtract. That's cool with me. That's going to be -8. C2 is equal to -13. That's disgusting. 13/8. Okay. Remember, our original function was this, right? So you can always go back to that. And if you plug that in, you're going to get C1 plus 39/8. Oops, didn't hit shift hard enough. Equals 10. Well, this is 80/8. If you minus over, you're going to get 41/8. Think. So if you plug those in up there, you're going to get, obviously you can just stick it right there if you want to. But if I take C1 times 2, if I times that by 2, I'm going to get 41/4 e to the 5t. And then C2 is 13/8, so that's going to be minus 13/4 e to the -3t. And this is x, and then y is C1 times 1 is just 41/8. Again, that's a 2-to-1 relationship, top to bottom. And then it's going to be 3 times C2, so plus 39/8 e to the -3t. And you are done, my friend. But again, because those are opposites, 5 and -3, they're opposite signs of one another, this will be a saddle point scenario. If you were to graph these guys, for instance, x versus y, and you could get a table of data, which that sounds like a job for Excel, Mr. Groom. I know, right? I know, right? So what a guy could do, of course, alright, is he could, put in some values for time, because of course it's all about time, yo. So I'm going to go like -10, -9, -8, -7, what? And these are my times, so I think I'm going to insert a row and put a T up there just for grins. Bam. T. And then a little X action, little Y action. And then down here, let's go drag these guys down a ways just for fun. Go a little more just for grins. One more time. That's too much. All right, now. What is X? Well, Mr. Groom, you said it was equals negative. Oops, I can't do this, so I need to do this. Let's do this, yeah. So it's going to be, well, that's disturbing. Come on, where'd it go? There we are. Yeah, let's do this. So equals 41 divided by 4 times EXP of 5 times T. Alright? Minus 13/4 times EXP of -3 times T. Booyah! Uh-oh. What did I do wrong? Yeah. Yes. What don't you like about that, you stupid... Oh, for gosh sakes. It can't be times, it can't be caps, Mr. Groom. Stupid computer. I don't know how it got to be caps. I don't remember capsulizing it. Oh, now what's your problem? Help on this calculation. I don't think I need your help, you stupid piece of garbage. Let's make it bigger so I can see what I did wrong. Okay, well, I think I know what the problem is. You get e to the 30. It's probably just freaking it out. So watch this. I think if I drag it down, it's going to be okay. Yeah, okay, we're good. The problem what happened is that, see what happens is it gets just too big and it just tells you to take a flying leap, okay? I should probably do it again here in a second. Well, maybe not, okay? So anyway, whatever. That's the idea. So notice what happens is as t is approaching 0, then this value, this function is getting smaller. It goes negative actually and then comes back up, all right? Same thing should be basically happening to y, correct? Let's make this smaller and do y as well. So equals 41 divided by 8 times exp of 5 times a2, right? Minus plus 39 divided by 8 times exp of 3 times a2. Booyah, right? That's a big number. Not really shocked by this. Copy it down. And it also came down to a minimum and so forth in the middle there somewhere. I wonder what would happen if we... not that one. It wouldn't like that. Hey, graph this crap that you don't know what it means, you stupid computer. Scatter plot. That's just disturbing. Yeah, it doesn't really know what to do with that. Maybe if I leave that last one off, I guess, maybe. Actually, let's do this. Let's go cancel this stupid graph. Go away. Okay. Grab these two dudes. Give them the old double tap-a-rooney. And what is your problem? You know what? I have about had enough of your foolishness. You just go away. No one asked for your opinion. Oh, you hooker. No! There. Yay! Which is probably its whole problem all along anyway. I was referencing the wrong cell because I'm an idiot. Alright, so here we go. Oh, that's too much. I don't want to graph them guys. They're too big. Okay. So insert, scatter plot, booyah. Right? And I think you can see down here before we get too carried away, we were coming down towards 0 and we shot back off. That's classic case of a what's the word I'm looking for? It's a classic case of a saddle point. So let's actually do this. Let's start up here somewhere, I guess. Yeah, let's do that. It'd be nice if we could actually see what the picture looks like a little better. Yeah, aha! So it's headed down. Shoo! Off she goes again. Remember, we are graphing population Y versus population X in this case. And that's classic saddle point behavior. We will see some others as we go along. This will get you started for today.